Morning. Okay, so what are we going to look at today? Okay, this is the last lecture that we'll have on differential equations before we move on to the next topic next time. So what I want to do today, I want to tell you what to do when you can't solve a differential equation. So this week and last week, we've been learning about how to solve differential equations, and actually it's been a little bit misleading in a sense, because I've only shown you examples that you can actually solve, right? We've looked at one type of differential equation, which are the separable kinds of DEs, okay? They're the ones that are fairly easy to solve, except that, of course, you still have to do an integral, okay? And we know that integrals are hard to do and sometimes, in fact, impossible to do. But even if you didn't have a separable DE, you might be stuffed, right? I mean, you might have no idea how to solve it. Even if you did have a separable DE, you still might not be able to solve it just because you don't know how to do the relevant integrals, say. So what do? Well, there are lots and lots of methods, right? I mean, solving differential equations is a very important thing, so there are loads of methods for actually doing it. And what we're going to do today is we're just going to learn about one of them, right? Which is kind of the simplest one, but already it's very common sense, right? It's kind of what you would think of if you wondered how to solve a DE, and you didn't know what to do. It's kind of the first thing you would try. And it's not the best method by any means, right? There are very, very sophisticated methods, but it does work. And it shows you already how these things can go. Okay, so this is called Euler's method, and here's the idea. Today the 20th? Yeah. Okay, so the idea is you want to you've got some formula for y dash, right? So your dE looks like dy dx equals blah, something, right? And you don't know how to get y out of it. Let's suppose at the moment it's just a function of x. So it's like dy dx equals something to do with x, but you can't integrate it, say. Okay, so what do? Well, you say to yourself, okay, suppose I know that, y of 0 equals 1, say, right? Suppose you know that. Right? That's your initial condition. And what you know is, dy dx at this point, right? Because you've got the formula, right? So your formula is dy dx equals something. Let's call it, f of x. Some formula that you've got, right? Because you've got the dE. But you don't know how to integrate this. And you know y of 0 equals something, say 1. Okay, you say to yourself, okay, well, what I can do is I can start with that point. I know that point is on the solution curve. And then you say, okay, well, I also know that at 0, right, I can put a 0 in here, and I can get the slope, right, of my solution. I know what dy dx is at 0. I know what y is at 0, and I know what dy dx is at 0. So I know the value, and I know the slope. Now, what kind of function is completely determined by its value at its point and its slope? Does anybody know a kind of function that's completely determined by those two pieces of information? Linear function, right? A straight line. If you know the slope and you know a point, you know the whole straight line, right? So let's just draw a straight line through this point with that slope, right? Let's just say this slope is, let's just say y dashed at 0 is something, I don't know, some number, right? Number. I don't know what the number is. Okay, let's call it m. Okay, let's draw, this has slope m. Right? Now that is not likely to be the answer, is it? Okay, because the answer is not necessarily going to be linear. But what you do know is, whatever the answer is, this is the tangent at that point. Right? Whatever the curve might be something like this. This might be the actual solution, right? Actual solution. Right? You don't know what the actual solution is, but you do know the tangent at that point. right? Because you know dy dx at that point. You've got a formula for dy dx. That's in fact all you have. So what you could say is, well, suppose I know, y of 0, right? That's given to me. If I want to know y of 1, right, that's up here. Okay, there's no way for me to find that out easily, but I can approximate this green curve with this black curve, and I could guess that this is my answer for y of 1. So this is the actual y of 1, right? That's the actual point, right, is here, right? And this is my guess. There. So you see what I'm doing? I'm actually replacing, I don't know what the solution curve is. I don't have the green curve, but I do have the slope. So all I'm doing is I'm just pretending the answer is a straight line, basically, and just using the value of the straight line to approximate the value of this actual solution. Okay, now it's not that good, right? Because, in this picture, this is quite a big gap, right? But if I had chosen maybe to ask here, what is the value here, and I'd approximated the green one with a black one, then they'd be pretty damn close, right? The smaller you ask for, the closer you ask for your approximation, the closer the value to 0, the better the approximation is going to be, right? Because that's how differentiable functions work. When you zoom in on very, very close up, they look like straight lines, right? They're approximated by their tangent lines. That's what it means to be differentiable. So over here, it's not so good, right? If I continued this black line over here, it could be very, very far from the solution. Could be way over here by now, right? If you go very far away, there's no reason why they should be the same. But if you just pick a very small step, okay, then they'll be pretty close. And in fact, the idea is, suppose you wanted to know this one now, right? What would you do? Okay, here's the actual answer that you want, right? That's y of 2 up here. Right over here, I guess, is y of 2. So what you do is you say, okay, well, I'm gonna do one jump to here, and then I'm going to say what is the slope at this point, right? Here's the thing. I don't know the value, but I do know the slope because I know dy dx. So the slope here looks like this. So I'll go from here, and I'll use the actual value of the slope and draw a straight line and get to here. That's my next guess, right? So you just kind of perpetuate this program, okay? You draw a straight line for a little bit, you make a guess, and then you start at that point and you draw another straight line, and the next straight line has the correct slope. That's the idea, okay? So here's another picture of it that you can see in your notes. Maybe a little bit difficult to see what's happening in this picture, okay? So the dotted curve is the actual solution to some dE, right? As in, it's the graph of a function, okay? And so what you're doing is you're saying, okay, at this point here, right, that's what I know, that's my initial condition, so I know that point is on the curve, and then you see this yellow line, that's the tangent, right? We know that tangent because we know the value of y dash, because it's a dE, that's what we have y dash, right? So we know y dash, so we use y dash, we sort of flow along y dash until we get to this point, and we say, okay, that's my guess for y of a, right, or whatever. That's my guess for y at this point. And then you say, okay, but I don't want y at this point. I want y a little bit further. So what you do is you start from here, and you see this is the actual value, right? You see this yellow line, right? That's the next tangent, right? You see this is parallel to that. So you go along however far you need to, parallel to this tangent until you get your next guess. Right? This is the real value. This is the guess value. Right? You want to go a little bit further. You look at the actual real tangent here, right, which you have the slope of, and you go parallel to that until you can get. So the point is you don't have the blue curve at any point, but you do have all the yellow lines, or at least you have the slopes of the yellow lines, and you can use that. So all you have to do is work out a formula for how to actually follow these lines. Right? Not so hard, because you know that if you go, say, a distance h, so you know y of a, you want y of a plus a little bit, right? Y of a plus h. Okay, well, how far, the only question is, right, you go across h, how far up do you have to go? Well, the slope of this yellow line is y dash, so if you've gone across h, you need to go up h times y dash. It's the rise over run, right? So what is the, if you work out the slope of this line here, it's hy dash divided by h, right? Rise over run. So you divide this by this, and you get y dash. So if you've gone over h, you go up hy dash. So this point here, right? So over here, this point, right, your guess point is y of 0 plus h times y dash of 0. In our case, h was 1, right, because we went across 1, but you don't have to go across 1. So if you start at the point A, right, if you start at the point A, sorry, I can't see what I'm doing, and then you want to go over to here, A plus a little bit, right, and this is the value you've got, and this is your actual solution, right? You don't know what that is, but you do know the slope at that point, right? That's your guess. Then this distance here is h, and this distance here is h times y dash to a. Yeah? And the y value here is y of a, and the y value here is this plus this height, y of a plus h y dashed of a. So that's the scheme, right? That's your next guess. There's a formula for making your next guess. And the idea is you start, at the value you know, and you make h small so that your guesses are close, and you do lots and lots of guesses, right? So if you started at, you knew the value at 0, and you wanted to know the value at 1, right? You wouldn't just do one step. That would probably be really bad. You do like 10 steps, all of size 0.1, right? The smaller the steps, the better the approximation is going to be. Okay, so let's try it. We'll try it on a DE where we can actually check the answer, right? One that we can solve. Okay, we'll see an example. We'll do one that we actually can solve. That way we can check the answer. We can see how accurate it is. Okay, so here we go. Y dashed is x squared. Okay, that's easy DE to solve. Easy to write down the general solution. Okay, y of 0 equals 2. So this is an initial value problem. There's exactly one function that solves this initial value problem, this differential equation with this initial condition. Okay, we'll solve it in a minute. Let's just use Euler's method to get an approximate solution. Okay, so we want to know what is y of 1, okay, and yet let's use one step. Okay, use one step. So this means h, the size of the step, is going to be 1, because we want to go from 0 to 1 in one step. Okay, so let's see. We know y of 0 is 2. Okay, that's given to us. So we need, and we know y of 1 should be y of 0 plus h times y dashed of 0. That's the formula, right? So it's exactly like what's up here, right? So you want to know y of, so this is equal to y of a plus h, right? The value here. So if you want to know what it is at the next step, you do what it is at the previous step plus h times the derivative. Okay? So if you want to know what y of 1 is, so this is 0 plus h, because h is 1. You do y of 0 plus h y dashed as 0. Okay, so what are these values? Y of 0 is 2, h is 1, y dashed of 0, right? This is y dashed. We put a 0 in there, you get 0 squared. Right, this is 1 times 0, so it's 2. So that's our guess. Actually, our guess is the same as its value at 0, right? Why is this the guess? Well, let's just check how close it is. It's obviously not the right answer. Let's just check and see what's going on in this example. Okay, so how close is this? So How accurate is this? Well, what's the actual solution? Y dashed equals x squared implies y is a third x cubed plus c, right? That's the general solution to that dE. Okay, y of 0 equals 2 implies 2 is 0 plus c, so c is 2. So the actual particular solution is y equals a third x cubed plus 2. So there's the actual solution, right? And the question is, what is y of 1? So y of 1 is a third times 1 cubed plus 2, which is 2 and a third. So it's not 2, but it's not that far from 2, right? It's pretty close to 2. What actually happened in this example, why was the guess equal to the same value at 0? Let's have a look. So the solution here looks like this, right? Here's 2. A third x cubed looks roughly like this, right? That's the actual solution to this dE, a third x cubed plus 2. Okay, and what did we do, right? Well, we tried to say, okay, we know this value, we want this value, right? So the actual value here is 2 and a third. Okay, this is obviously not to scale. That's 2. That's 2 and a third, yeah? Okay, so this is the actual value here, right? What did we do? How did Euler's method work? Euler's method said, let's take y of 0 plus 1, which is h, times y dashed at 0. Right? That's like drawing the tangent line and moving along the tangent line a distance of h, right, on the x-axis. What's the tangent line here? This graph is flat at this point, right? So there's the tangent, right? That's the tangent. And so here's our next guess. Look at that. It's exactly the same value. It's 2 because the tangent is flat, right? That's why it didn't come out so good. But it is the scheme, right? That's what the scheme is. I mean, if we didn't want to go 1, but we just wanted to go like 0.1, well, this graph is actually pretty flat around that point, right? So if we wanted to go 0.1, our guess would still be 2, but the actual answer wouldn't be 2 and a third, right? It would be like 2.03, much closer to 2. So if h was smaller, this would actually give a much better guess. Okay, so there's a picture of what I think is happening in this example, right? I think the green one is the actual solution. The black one is what Euler's method is trying to tell you to guess, okay? And you're actually getting the same value as over here because that's a flat line, but this is the real value. Okay, so let's have a look at what would happen if we made them smaller. Right? So we'll do the same example, okay, but we'll use 2 subintervals. So we'll do gaps of 0.5. Okay, so the usual way so this time, same, but h equals 0.5. So this time we need 2 steps. Okay, so an easy way to set these problems out is to draw a table. Okay, so we'll put this data in a table. Okay, so the value of x we're interested in, the value of y at that point, the derivative at that point, right? In fact, maybe what I'll do is I'll do h times the derivative at that point to make life easier, and then the next value, right, which will be this plus this. Okay, so this is all the information we need because we're going to start at x equals 0. We know that exactly, it's 2. Then we want x equals 0.5. And then finally, we want x equals 1. So what we do is we go along here, we fill in this information, and then this number here becomes the next value here. Right? So h is 0.5. So what's y dashed? Y dashed was x squared, right? Okay. So y dashed is x squared, so that's 0 squared, and h is a half, So a half times 0 squared, which is 0. So this plus this is 2. And then this is our guess for y of a half. Right? You see how it works? So you go along the table, and the last entry is your next guess. Right? So 2 is the next guess. And then hy dash. So y dash is x squared. Okay? Oh, sorry, y dash is x squared. A half squared, that's x. Times h. So this number here is an eighth, because that's a quarter and that's a half. And so now you add these together, you get 2 1/8. Right? And that's your next guess. Okay, so you see this time it gave us something closer to the actual answer, which was 2 1/3. Right? Before we got 2, which is a bit too low. Now we're getting 2 1/8, which is also a bit too low, but it's closer. Right? If you did this again, okay, with you know, with 10 intervals, you know, h equals 0.1, and you did it 10 times, you'd get even closer to the answer. Okay, so if you want to sort of play with this and just see, you know, a whole bunch of steps done and all the numbers laid out, okay, you can actually do that. If you go over to my uni, in the study guides, okay, it's week 4 this week, I think. So under week 4, right under the study guide, I've put a little link. Okay, it's called Euler's method. So what you can do is you can click on it, and here's a little sort of app that you can play with, right? So what you can do is you can put, it's a little bit hard to see actually. Okay, so you can see here, right? I don't know if you can see that very well. There's a box. It says dy dx. And you can put whatever function you want in there within reason, because it has to actually solve the dE. Okay, so what's in there at the moment is x plus cos x. So the solution to that will be something like x squared plus sine x, right? In fact, if we wanted to see it look a bit more funky, we could do something like 0.1 times x plus cos x. Okay, there you go. That's a bit more funky looking. Okay, so the blue dashed line is the actual solution, right? Notice it looks like a parabola that's a bit wavy because it's x squared plus sine x, right? Okay, and you can set the step size as well, right? So the smaller the step size, see those dots? They are the guesses that Euler's method is giving you. Okay, the smaller the step size, the closer they are to the actual curve. If I make the step size really big, by the end they get a little bit away from the curve, right? Here they're a bit big, they're a bit off, right? Let's go back to one where we can see. Okay, so in this one, okay, what you can see is that it starts out exactly on the curve because that's your initial condition, okay? And then it gets a bit off the curve, okay, because the step size is so big. If you make the step size smaller, right, see how they follow the curve really closely? So if we did more steps to get all the way over to here, right, it would actually follow the curve much more closely than if we just had a big value of h. Okay, and you can see all the stuff laid out exactly how we had it. Whoops, there's a little spreadsheet here that I've now lost control of. Right. Oh, come on. Okay, a little spreadsheet here, right? It says x, y of x, hy dash, y of x plus h, which is the sum of these two columns, right? And it's just running, you know, it's running 15 times. Okay, so you can play with that, right? You can put in any function you want within reason here, right? Function of x, and it will give you the actual solution if it can, plus Euler's method. If you put in something too crazy and it can't integrate it, then it will just give you the solution. It will just give you the approximation. It won't give you the solution. Like if we try ln of x times cos of x squared or something, this is junk. It'll never be able to do that, surely. Nah, look, it's not even going to, oh, because I put a -5 in, that's why I can't do it. Let's make it 5, 5. So here is an approximation to the solution curve. It looks a bit like a scatter plot. I can't even tell what, it's wavy because of the cos x squared, right? There's a very small amount of that curve, right? See, it's going all over the shop because this is a complicated DE, right? And we're trying to make h really large here. And it can't draw the actual curve because you can't integrate that function. It's too hard to integrate. Okay, but you can play with that, right? You can check out, put in a few different functions, put in ones you could test yourself. It'll show you the solution, show you the actual solution curve, and it'll show you Euler's approximation to it as well. Okay. So what I want to do is give you a chance to run this scheme. Just try and run this formula, right, by yourself. We'll come back and I'll show you in a minute. We'll do another example, which I'll show you what else this can do. Okay, but first I just want to give you a chance to have a go at it. Okay, so here. Okay, so here's a question. I've given a simple DE. Okay, and I just want you to do one step, right? So h is a half, that's the size of the step. Just see if you can use that formula to get one step. Okay, you'll need some paper for these ones today. You might need to write this down. So here's a minute, right? Get out some paper, have a go, see if you can work out which one of those answers is the approximation that Euler's method gives you. Don't worry about the actual solution, don't care what that is. Okay, 10 seconds. Answers in. I mean, once you know how to do this calculation, it's quite simple, but you may not have had quite enough time to do it. That's okay. Which one are we doing? This one. All right, let's just see what people thought. Wow. Okay, so either people are slightly confused about the formula or they didn't really have enough time to check everything. Okay, have another go. Talk to the people next to you. Show them what you wrote on your paper. Have a look what they wrote. Okay, I'll reset it. Okay, here's a couple of minutes to talk about it. Okay, answers in. Let's have a look. Okay, so still a little bit of a split, but A is taking over now. Let's do the calculation. So here's the formula, right? Y at some point, y at x plus a little bit is going to be y at x plus h times y dash at x. Right? That's the formula. Okay, we had A's before, doesn't matter. The point is, you know it at this point, X, you want to know it at the next point, X plus a little bit, and that's the little bit. In this case, the little bit is a half. So Y of a half is Y at 0. 0 is what we know, H is a half. Right, we just need this information. So this we've got, it's 1, that's given to us. And this we have to actually calculate. This is the only thing you have to calculate. You've got a formula for it. You just put in the value you need. That's the only key, right? You need the value 0, so you put it in, you get 0 on 2. So it's 1. So good job. Before there was a bit of a split. A was actually the least popular, but now it's the most popular. In fact, this is exactly the same as what happened before, right? The slope at 0 is flat, which is why it's giving you the same value that it did before. Right? If I made this x on 2 plus 1, say, right, then y dashed of 0 wouldn't be 0, it would be 1, right? And so then that would actually change things. Your guess would be, 2 or 1.5 or something. All right, excellent. So here's another one, okay, to have a go at. This one is a bit different. Okay, you don't have to do any calculations for this one. Just take a look at the pictures. Okay, it's a bit hard to see, but the blue curve is the actual solution to some DE. I can't remember what the DE is. That looks like a sine curve, so maybe the DE was just cos, dy dx equals cos or something. Okay, but then the black lines are a picture of Euler's method being used to get the red cross, right? This is the final estimation from Euler's method. Which one of these is actually correct? Which one of these is actually Euler's method? 3 of them are just junk pictures that I drew. 1 of them is actually Euler's method being used with 4 steps. Okay, have a think about it. Don't talk. I'll give you a chance to talk in a minute. No talking. Thinking. Okay? You probably don't have to write anything for this one. Just have a look. Think about it. You've already seen some pictures of it. And I'll give you a chance to chat about it in a second. All right, 10 seconds. We actually got quite a lot of responses for this one. That's good. Let's have a look. I won't let the timer run down. I think that's probably okay. Okay, most people going for B. B is this one, right? I don't think I even need to give you a chance to talk about that. It's absolutely correct. What? Oops, pushed the wrong thing. Cancel. Answer B. Okay, so let's have a look. Why is it B? What's wrong with A? Does someone want to tell me what's wrong with A? They're not connected. Yeah. I mean, what's happening in A is that you've got the correct slopes at each point, but then you're starting at the actual value, right? You're starting on the graph. The whole point is you don't know what those values are. You don't know the blue curve. So if you wanted to run Euler's method, you could make this guess for here, right? You could make that your first guess. But how could you possibly start this curve to get this guess here? Because you don't know that point. You only know this point. So these ones here, the tangents start on the curve, which is no good, because why would you bother drawing all of this if you already knew that point? Okay, what's wrong with this one? I mean, again, the slopes are correct, right? But what's happening here? They're just all starting on the x-axis. You're not feeding in the value of y you just found, right? So you start here. This is your value of y. And then you're ignoring that, and you're just starting down here again. That's not the right thing to do. Euler's method says you take the previous value of y and you feed that in to get the next value. Okay, what's happening here? I mean, sorry? They're not even the tangents. Yeah, this is just junk. I mean, this picture is just like a polygon approximation to that, right? I mean, I just drew like secants or whatever these are called, chords. And it actually gives you, I mean, if there were a method of approximation that could produce this, right, without knowing the answer, that would be incredible because it's actually the correct answer. So that's junk. But this one here is correct. You're drawing a tangent for a bit. This is your next guess, and you use that as your starting point to draw the next tangent this gives you the next guess here, and then you draw the next tangent, right? That's this one, to get to here, and then you draw the tangent at this point, you start it here, and then that's the value you'd actually get. All right. Okay, so that's kind of what Euler's method can do, right? We've seen how it works. Actually, it can do something slightly more sophisticated, because what we saw, I mean, what we've done so far is we've solved two kinds of DEs. Really, it's kind of one kind of DE, but they look a bit different. So what are the kinds of DEs we've solved? They're separable DEs. So this includes the kind where you've got dy dx equals f of x, right? Like what's written up there. So if you have something that looks like dy dx equals f of x, right? That actually is a separable DE. There's just no y dependence. So, you know, the y is already separated for you. The function that's y is just 1, right? The function of y is just a constant. And this is the function of x. So that is actually a special case of a separable DE. But in general, separable DEs are more complicated. They have y's and x's in them, right? We know we can solve those, but the problem is that, you know, you still have to do the integral, and sometimes you just can't do it. Okay, so Euler's method can also be used when the DE has a y in it. You know, so if it's dy dx equals something to do with y and x, that's a much more complicated situation, but you can still use Euler's method, right? You just have to feed in the value of y and the value of x when you work out the slope. That's the only difference. Okay, so let's have a look, right? Here's an example. Okay, so suppose we had, okay, suppose here's the DE, right? Y dashed equals x plus y. That's actually not a separable DE, okay? So as far as we are concerned, this DE is impossible to solve, right? We can't solve this DE at present. It's actually not so difficult to solve. I mean, it looks fairly simple. You'd hope that if we knew anything about DEs, we could solve this one. And in fact, we can, right? So there are methods for solving this, but not available to us because it's not separable. Okay, so we're on our own, so we better use some other method. So let's suppose that we know, where are we? So y of 0 equals 1. That's our initial condition. Okay, we want y of 0.5. So we could use one step, right, of size 1/2, but that's not going to be very good just because it's such a big step. So better to use many little steps. So let's use h equals 0.1 and 5 steps. Okay, so let's set it out the way that we had before. So here's the value of x, okay? It's going to start at 0 because that's what we know. Okay, here's y at that point. Okay, we know that's 1. So that's the information we have. Okay, then what we need is y dashed. Okay, so let's do what we did before and we'll write it as hy dashed. But this time, it's not just y dashed of x, because y dashed depends on x and y. So it's really y dashed of x and y. Right? And then what's in here will be the next guess, y of x plus h. What is that? That's, well, this is our guess for y of x plus h, which is y of x plus h y dashed. Okay, so this is really what we're putting in here, right? Okay, so you see the scheme, right? You start with the value of x you're interested in, so the next value will be 0.1. The next value after that will be 0.2, 0.3, and we want to go all the way to 0.5, ideally. We may run out of time or energy, but let's see how far we can get. Okay, so what we need for, and h is 0.1. So all of these are going to be like 0.1 times something. And what is the something? The something is what you get by putting these two numbers in this formula, right? It says h times y dashed. Y dashed is x plus y. Here's x, here's y. So in this case, x plus y is 1. So this is 0.1 times 1, which is 0.1. So this is 1.1. Job done. Right? So that's your next guess. Right? It's your next guess for y is 1.1. Okay. So now we need to know what comes next. So y dashed, right? Our guess for y dashed at x equals 0.1 is x plus y. So it's 0.1 plus 1.1. X plus y, 1.2. So this is 0.012. Sorry, this is 0.12. This number here is 0.12. So we add it to this, and we get 1.22. Right? This is this plus this. Okay, that's our guess for here. So is everybody following so far? Right? You've got, so what you need at each point you're interested in, right? At each x value, you need the x value, the y value, that is your guess at that point, the slope, or h times the slope. That tells you how much further you need to go for your next guess. Then you add these two, right? That gives you your next guess, right? And then this number goes in here. So for 0.2, right, x equals 0.2, our guess for y of 0.2 is this, right? What is our guess for y of 0.3 going to be? It's going to be 1.22 plus this. This is going to be h times, put these numbers into here. In the previous examples, right, the first example, we didn't need to put this number in. We only needed to put this number in, right? Because y dash was only a function of x. So this is a bit more complicated because y dash is a function of x and y. But it doesn't matter. We've got an x and we've got a y, so we put them in. This, in principle, could be a bit less accurate than the previous one because this number is not totally accurate, and we're using that to generate the next slope. So this is a bit more dodgy, right, than the previous one. It's probably going to go awry quicker. But that's okay. The method still works. Okay, so x plus y is 1.42. And so you times this by 0.1 and you get 0.142. And you add it to this, right, add these two together, you get 1. What did I say? 0.142, 1.362. Right, that's our next guess. Okay, and we keep going. Do you want to keep going? I think that the student exercise immediately after this is to finish this problem. Oh, there you go. So some of the values are already filled in there, right? They're the ones we've just calculated. Okay? So, see, this student exercise is to finish this problem, right? Under the assumption that we would either run out of time in class or get too bored. But I think it might be worth... so maybe we'll just do one more step, right? We'll do one more step. And then I'll let you have a go at just checking that you understand this yourself. So, okay. So the next thing we need is y dashed, which is x plus y. So it's this plus this. It's not always this plus this, right? Depends on the formula. Depends on the formula. In this case, it's x plus y. So this plus this. So it'll be 0.3, so it'll be 1.662. And then this is 0.1662, so it'll be like 1 point something. This is why I didn't want to do this one. 452 something. 5282. Right, that's our guess for, that's y equals, y of 0.4 is approximately 1.5282. Right, so if you run that scheme one more time, whatever you get here, that will be the answer. Okay, so this student exercise is almost done for you now, right? You just need to do one more to get this number here, and that's your guess. Okay, so rather than doing that, I'll give you, I've got one more thing for you to try out. It's okay, it's the same scheme, okay, but just the numbers are a bit easier. Okay, so again, get out a piece of paper and have a go. Right? I'll give you a minute. Okay, I'll give you a minute, and then if people don't have their answers in, I'll give you a little bit more time. That's okay. Okay, get out a piece of paper, have a go, and see if you can run this scheme. Now, you only need one step here. Okay, so I want y of 1, step size is 1. So you only need to do one iteration. You don't need to do a whole table's worth. You can still set it out like that. Okay, there aren't so many responses, so I'll just give you a little bit more time. Okay, the numbers are fairly easy here. Okay, and then we'll have a look at what everybody said, and we'll see, and I might give you a chance to chat about it. All right, let's have a look at what everybody thought. Okay, so it looks like most people are gravitating towards the number 2, so that maybe that was enough time to actually work it out. A few other answers. Stop. You're just going to put in the number 2 now. Stop. Okay, let's have a look. Let's just have a look whether this is the correct answer or not, right? I don't think we need to. Don't think I need to give you a chance to talk about it. So it should be, right, x, y, h times y dash, right? So this is x, y at x, h times y dash at these two values. You need both of them this time, and y of x plus h, the next one. Okay, so we start at 0. We know y of 0 is 1. H is 1 in this case, so that's very easy, right? 1 times, and what's y dash? We put these two numbers into this formula, right? So it's 2 times 0 plus 1, right? That's 1, so this is 1 times 1. 1 plus 1 to get here is 2. So it is in fact 2. Good job. So you see how the scheme works, right? It's just a matter of iterating this. If I asked you for h of 10, you would do that 10 times. If I asked you for h of 1 with a step size of 0.1, right, you would change your h and you would keep doing it 10 times until you got to h of 1. Okay? Of course, in practice, you wouldn't actually do that. A computer would do it for you, right? And it would do like many steps, right? Way more than you could do on paper. But the point is, I want you to know how the method works, right? I want you to be able to demonstrate that you understand how to run the method and you know which calculations need to be done and you can actually do them yourself. All right, very good. So we meet again on Thursday. We start a new topic, okay? Notice that if you go back to the beginning of this section, okay, on DEs, you can now look through the list, right? Here's the list. By the end of this chapter, you should, if you look through that list now, you should know at least what all those things are, right? You should be confident that you could actually do those things with what you've learned, and if you keep practicing. All right, make sure you can. See you on Thursday.